Let's get started again. Our next speaker is Jeff Mozzochi, speaking on the circle method.
I want to thank Mel and Kevin for inviting me. And these guys organize these things so well that it makes it look like it's very simple. But there's a lot of work to it. And they put up with me. And so that's. Now we're going to go back to 1921. So bear with me. Oh, this is not writing. There's more of it. Thank you. Right. Over N, and then
I'm sorry, what is the first?
I'm sorry.
What does the first expression say? I can't.
Oh, okay.
E of X
E
equals
is either
two pi r.
either 3 pi r.
Oh, well, I know that. I didn't see it though.
Yeah.
Sorry.
And then the number of primes. By the way, we're doing this for any even integer, not just m equal 2, but for any even integer. Okay, so that should be a. All right, so now this is the number of prime pairs vi. And then we have an integral representation for this. From x naught to x naught. And then this function squared. And so the circle method is you break this up into two integrals. Well, first let me say one other thing here. Over here. Now we're going to consider all the fractions h over q, where q is less than or equal to log 15n, and hq is equal to 1. And so it turns out a fellow at MIT many years ago did me a big favor, and he analyzed this on a computer. And these things, this function right here, squared, spikes right up, so we're gonna have, and these are gonna be our major arcs. And then what's in between them are the minor arcs. And now we're going to break this interval up into two parts. This is little M. And then plus cap and then
Excuse me.
the problem with some of them. Sorry?
Let's try and switch out for a better marker.
Okay. Thank you. And we're going to sum this.
Yeah.
To and then we're going to write this over all the sum of over all these fractions. Summation u less than or equal to log 15n DHU and HQ equal 1. And then THQ
There's some new markers on the table there. One's, not that one, the other two.
not that number. Okay, now. Can I erase this?
Yes,
So what happens is this. After about 4 pages of calculation, we wind up with this. This is the minor arc. Plus SPN and then plus where S is just a constant greater than 1 and Tn is the summation log minus 1 M1 log minus 1 M2 M1 less than or equal to N M2 less than or equal to N and M2 equal M or even M. Now, if we divide every term and of course, so this is the heart of the whole matter. So we have 2 cases here. Oh, by the way, this is greater than or equal to 10 over log squared. And this is a very tight situation here. But there's no problem because this comes out of an asymptotic expansion. So you have a pretty big C here. But it is kind of strange where you have the same order of magnitude. So now we have some cases.
well, what is the goal? What is the,
I'm going to come up with a sufficiency condition
for,
for the number of the M prime conjecture that there are infinite number of M primes.
M primes in a certain configuration?
No, just look, the twin prime conjecture says there's an infinite number of twin primes. The M
Oh,
prime,
the difference M, 2 primes differing by M.
sorry,
2 primes differing by M.
yeah,
Oh,
oh yeah. Now, let me erase this. So here's what happens. Let's consider the case where this is finite. So there's not an infinite number of m primes. Well, if that's the case, this term goes to zero. Of course, this term goes to zero by definition. And so now, if you think about it, you have s greater than 1 here, and you have, you have t sub n. Yeah, let me write this clearly. We have t sub n equal to that. And t sub n t sub n greater than n over log squared n. And less than a constant n over. So what happens if this goes to zero? Then the minor arcs are forced for all n greater than n of m, the imaginary part has to be, I'm sorry, the real part of all of the mn's has to be negative. And that's a pretty strange. In other words, if this thing here is finite, this term goes to zero. And because we have this condition and this condition, if you think about it for a while, for all n greater than some n of m, the real part of all of the minor arcs have to be negative. So a sufficiency condition would be that there's an infinite number of mn's such that the real part is positive. In other words, that would be a sufficiency condition. And I claim that that's a lot more plausible than the Hardy-Littlewood condition, which says Mn is little o Now, I've thought about that for a long time, and I have no idea whether that's true or false. Okay? I mean, I don't know what they say is that if the sequence of m and n satisfies that, you get the twin prime conjecture and you get the m prime conjecture. I think this is a lot more plausible. That there are an infinite number of minor arcs so that the real part of each minor arc is positive. That's certainly conceivable, right? Now, what happens if let's just say this is true, that there are infinite number of m primes. two cases. When you divide this by n over log squared n, Hardy and Little would say this is less than or equal to a constant, and less than. In other words, Hardy and Little would conjecture that if the twin prime conjecture is true, this ratio is going to be bounded between two constants, and if that's the case, you don't have any problem here at all. But if for some reason this ratio goes to infinity, then you're immediately forced into the situation that there is an n such that the real part of all of the mn's greater than or equal to that is positive. Okay? Which means my condition here is necessary and sufficient if this ratio goes to infinity. Now, I think this condition here, since it seems like it's totally unreasonable, Hardy and Littlewood are probably right that this ratio is bounded. Okay? So to sum up, what I'm proving here, believe it or not, my handwriting is terrible. A sufficient condition for the M prime conjecture is that there are an infinite number of minor arcs whose real part is positive. And that's very plausible, I think. You know?
You haven't proved that yet.
Oh, no. But I mean, I don't know how you feel about this, but after looking at this for 30 or 40 years, I don't have the slightest idea whether this is true or not. Okay? I never met anybody that does. Now, and also I think that this makes Hardy Littlewood very believable, where they say, well, two ways to say it. This is asymptotic to that, or the ratio is bounded. I think that gives more believability to their statement. So thank you.
Thank you, Jeff. Anyone not believe? Yes, but then the n over log squared. Okay.
But maybe other side.
But you haven't proved it yet.
I have.
Yeah. Thank you, Jeff.
Oh, thank you. I apologize for my sloppiness.